Hello, everyone, and welcome to this screencast lecture on the human muscular system, part 2. This is chapter 10. In the previous lecture on the muscular system, we focused primarily on the anatomy and physiology of skeletal muscle tissue and skeletal muscles. However, in this screencast, we're going to focus more on how skeletal muscles produce body movements. When we talk about how skeletal muscles produce body movements, there are going to be four principles that apply that we're going to be addressing in this screencast. The first of these is we ask ourselves the question, how are muscles attached to bone? So we'll talk about that. The second principle is how muscles are associated with leverage systems and mechanical advantage. Our third principle is going to be muscle actions, and we'll talk about what we mean by actions as we move along. And then finally, we'll address how skeletal muscles are named. So let's go ahead and get started. First of all, let's talk about muscle attachment to bone. So each muscle has two sites of attachment on the bones. One site of attachment is called the origin. The origin is defined as the proximal site where the muscle is attached to a more stationary bone. So as we take a look at this muscle over here, this is the bicep muscle, and we take a look at the bicep muscle, we can see that it's attached to the bones in two sites, one here and one down here. Now as we take a look at these attachment sites, we can see that this attachment site is more proximal, because what does the term proximal mean? It means closer to the root or origin of the limb or the extremity. So this is the area that's closer to the root or origin, and the attachments are on a more stationary bone, the scapula right here. And actually biceps means two heads, and each head has its own site of attachment via a tendon. One tendon attaches to the scapula right here at about the superior rim of the glenoid fossa, and the other tendon attaches right here on this little finger-like projection that we call, remember, the coracoid process. Okay, the other side of attachment is referred to as the insertion. The insertion is defined as the distal site where a muscle is attached to a more movable bone. So as we move along the muscle here, we move further and further away from the site of origin or the root, and we're moving further away, so we're moving distally. So this distal site, we can see that the muscle attaches to two places, here on the radial tuberosity and also here on the neck of the ulna, just below the trochlear notch. All right, so these are two sites of attachment, one proximal and one distal. Now you have to be careful though with these definitions. There are actually two important concepts to note in these definitions. One is proximal site, and the other is, or let's take a look at the origin. First of all, we notice in the definition of origin we have two important concepts. One is proximal site and the other is stationary bone. Both of these come into play. The origin is the proximal site and or may be either the proximal site and or the stationary bone, while the insertion may be the distal site and or the site of attachment to a more movable bone. So here in this bicep muscle, we can see that the origin is both proximally located on the limb and attached to the more stationary bone. And the insertion is located here distally on the radius and ulna, but also the radius and ulna are much more movable bones. But let's take a look at a second scenario. Here's a muscle called the sternocleidomastoid muscle. And we can see the sternocleidomastoid muscle has two sites of attachment. One here, up on this little lump behind the ear on the skull, which is called the mastoid process, you may recall. And the other two sites down here, one on the sternum and one on the clavicle. Now, which is the origin and which is the insertion of this muscle? Well, remember, in this case, we're not on a limb, so we're going to have to apply the second component of each definition, which is for the origin, stationary bone, and for the insertion, movable bone. So down here we can see where the sternocleidomastoid process or the sternocleidomastoid muscle attaches to the clavicle, which is a more stationary bone, right? It doesn't move much, and then attaches to the sternum, a much more stationary bone. But as we move up along the sternocleidomastoid, we can see it has a single attachment site to the mastoid process. And the mastoid process on the head is a much more movable process of that bone. So the mastoid process becomes the insertion of the sternocleidomastoid bone. So I hope that makes sense to everyone. All right, next up, between the origin and insertion, we have the portion of the muscle which is the thickest part of the muscle, and it's referred to as the belly. Now you might want to write this down. It comes by some other names as well. It can be called the head. It can be called the gaster, G-A-S-T-E-R, or it could be called the sept. Sept, belly, head, gaster all mean the same thing. It's this thick part of the muscle between the origin and insertion of the muscle. Now, as to our second principle, we want to take a look at leverage systems and mechanical advantage and the association of the skeletal muscles with those. Let's take a look at what a lever is. Leverage suggests levers. A lever is a rigid rod, is defined as a rigid rod that moves around a fixed point, and that fixed point is referred to as the fulcrum. In producing movement, the bones then are going to act as levers, and the joints are going to act as the pivot point, the fulcrum for those levers. Now, levers provide us with two advantages, and it's important to keep these in mind. First of all, a lever can allow a given effort to move a heavier load, or a lever can allow a given effort to move a load further than it otherwise would. Okay, with that in mind, let's take a look at the four components of a lever so we can understand this in more detail. The first component is the rigid rod. The rigid rod is comprised of the bones, as we mentioned. Then it's the fulcrum. The fulcrum is the pivot point, and remember, the pivot point in the human body for the levers is going to be the joints, primarily the synovial joints of the body. The effort is once again going to be the applied force that's going to cause the movement. The effort is going to be applied by contraction of the muscle. Remember, when muscles contract, they produce tension or pulling force. That tension or pulling force is going to be applied to the bones, and we're going to refer to it as the effort. And then final component of the lever is the resistance or the load. The resistance of the load is always going to be the object that's being moved or the weight that we want to overcome in order to be able to move the body part. This is the classic example of a lever, the teeter-totter example. Here we can see the board representing the rigid rod, the fulcrum, the pivot point, the site of application of the effort, and the load that or resistance that we're trying to overcome. Now, whenever we take a look at skeletal muscles and leverage, and whenever we look at levers themselves, not all levers are the same, right? So we talk about three different classes of levers. And each class is based upon which component of the lever is located in the center. So we have first-class levers. First-class levers, the fulcrum, the pivot point, is located in the middle between the resistance and the effort, as we see here in our diagram. Effort on one side, resistance we're trying to overcome on the other side, the pivot point in the middle. The next is a second-class lever. Second-class levers, the resistance now is located between the fulcrum and the effort. So we have the fulcrum here on the left, the resistance in the middle, and the effort on the other end. This is the classic wheelbarrow type of scenario that we have. And then finally, we have third-class levers. When we take a look at third-class levers, the effort now is located between the fulcrum and the resistance. So here we have the effort in the middle. Now, if you have trouble remembering these, and I mentioned before that I'm not a great memorizer, so I use a lot of mnemonics to help me remember things. So here's one that I developed for myself, and I'll pass this along to you that you might be able to use. Just think of the word free. In the word free, F is the first letter, R is the second letter, and E is the third letter. Notice in a first-class lever, the fulcrum is in the middle. So the F in free, which is the first letter, stands for first-class lever because F is first, and in a first-class lever, the fulcrum is in the middle. R is the second letter in the word free. In a second-class lever, the resistance is in the middle. So each letter tells us what's in the middle. For a third-class lever, the effort is in the middle, and when the effort is in the middle, that's a third-class lever. Okay, so that may be able to help you. Let's see if it does help you. So let's take a look at these diagrams of muscles and levers in the human body and see if you can identify which class lever is being represented here. So here's our first diagram, and we have the muscle, the trapezius muscle, being attached to the back of the skull. And the trapezius muscle is going to provide the effort whenever it contracts, or what we might also call the applied force. The fulcrum is going to be right over the foramen magnum. It looks like it's right over the mastoid process, but actually it's right about the foramen magnum, which is the exit point for the spinal cord, right? And then the resistance is going to be the weight of the bones of the face. Okay, so we want to complete this movement. We want to lift the face up, and the pivot point is going to be right here at this point. So now we have the fulcrum in the center. If the fulcrum is in the center, what type of lever is this? It's a first-class lever. Free, first letter in the word free, is F, and in a first-class lever, the fulcrum is in the middle. See how it works? Okay, let's try another one. So here we have our second scenario where we have an individual who's going to stand up on his tippy toes, lifting the weight of the body. So as we take a look at it, the effort, the applied force, is going to be provided by the gastrocnemius muscle, which attaches here on the calcaneal bone. The resistance is going to be the weight of the body. The resistance is going to be applied here through the center of the ankle. And the fulcrum is going to be on the ball of the foot. That's where the pivot point is going to be. So in this scenario, what class lever do we have? Did you say second class lever? That would be right. It's a second class lever because the resistance is in the middle. Remember, R is the second letter in the word free. So when the resistance is in the middle, it's a second class lever. And of course, here's our third example. And in this case, we have an individual who's holding a weight in the hand. Okay. And this time, the force is going to be applied by the bicep muscle. So the applied force or the effort. And the fulcrum is going to be the elbow joint itself. Now, here's an important understanding that you should have. When we talk about the applied force of the effort is always applied at the point of insertion. So here, let's see if we can get it to show up. There we go. Here's the insertion point here. So that's where the effort is technically applied. If that's the case, here's the joint, the fulcrum. The effort is going to be applied in the middle between the fulcrum and the resistance, the weight that we're trying to overcome. So this time, the effort is in the middle. If the effort is in the middle, what type of lever is it? It's a third class lever. Okay? So hopefully that helps you to identify which class of lever we're taking a look at. All right, now, anytime we take a look at levers, the idea behind levers is that they're either going to, as we mentioned, reduce the amount of work that has to be done or increase the distance over which the load is going to be moved. This has to do with what we call mechanical advantage. So mechanical advantage is defined as the amount by which a simple machine multiplies an applied force or effort. For levers, the mechanical advantage, MA, can be determined by dividing the length of the effort arm, L sub E, by the length of the resistance arm, L sub R. Or we apply the equation MA is equal to L sub E divided by L sub R. Now, to help you understand that definition, we've got to take a look at what we mean by L sub E and L sub R. So let's take a look at the length of the effort arm first. Here's our classical lever, here's our rigid rod, and here's our fulcrum in the middle. Let's say that we're going to apply effort right here to the very edge of this lever. Okay, and the fulcrum is in the middle. The length of the effort arm then is going to be defined as the distance from the fulcrum back to where the effort is applied. On the other hand, the resistance, let's say, is going to be applied over here to the very edge of the lever on this side. So the length of the resistance arm is going to be the distance from the fulcrum to the resistance, L sub E and L sub R. Okay? So we know how mechanical advantage can be determined. Once it is determined, we can then determine the amount of effort that has to be used to be able to overcome a particular load or resistance. So how do we do that? We apply a second equation, and this is the equation that we apply. Effort is going to be equal to the resistance divided by the mechanical advantage. Now, when we apply that equation, when the mechanical advantage comes out to be greater than 1, the effort is going to be multiplied and the resistance is going to be easier to overcome. However, when the mechanical advantage is less than 1, the lever is going to be better arranged for moving a bigger distance, or we might say for speed. We're going to be able to move it more quickly over a larger distance. Okay, so greater than 1, resistance is easier to overcome. Less than 1, better arranged for speed. All right, let's take a look at how this applies. Let me draw a kind of a stick figure diagram of the upper extremity. And let's place a 50-pound dumbbell in the hand that we're going to try to overcome that resistance. And we're going to attach the bicep muscle, and here's the bicep muscle, and here's the site of insertion along the forearm of the bicep muscle. Now, with that in mind, this arrow is going to point out the pivot point right at the joint. So this is going to be the fulcrum. The effort is always applied at the site of insertion. So this arrow is going to represent the site of effort, where the effort is applied. And then where the dumbbell is, we'll take the center through the dumbbell, is going to be the point at which the resistance is applied. With that in mind, what's this distance right here? That's the distance between the fulcrum and where the effort is applied. That's referred to as the length of the effort arm. So we now have the effort arm. And if we take this distance from here, from the fulcrum, out to where the resistance is applied at, that's referred to, remember, as the length of the resistance arm. Okay, let's put some numbers to this. Let's say the length of the effort arm, where this muscle attaches to the forearm at, the insertion point, is about 2 inches from the fulcrum. The length of the effort arm then is going to be 2 inches. The length of the resistance arm, let's say that the length from the fulcrum to where the resistance is applied is approximately 8 inches. So the length of the resistance arm is going to be 8 inches. With that in mind, what's the mechanical advantage? Can we determine that? Remember, the mechanical advantage is equal to the length of the effort arm divided by the length of the resistance arm. In that case, the mechanical advantage is going to be equal to 2 divided by 8, 2 inches divided by 8 inches. Or we can reduce that to what? 1/4. Let's convert that to a decimal point. If we convert that to a decimal, the mechanical advantage is going to be equal to 0.25. And if the mechanical advantage is equal to 0.25, can we determine how much effort has to be applied by this muscle at the insertion point in order to be able to overcome the weight of that 50-pound dumbbell and raise the dumbbell up toward the chest? What effort has to be applied? Well, remember, the effort is going to be equal to the resistance divided by the mechanical advantage. So the resistance is equal to 50 pounds. The mechanical advantage is 0.25. 50 divided by 0.25 is equal to 200. So this bicep muscle has to apply enough force to overcome the equivalent of 200 pounds. So this lever is not designed very well to make the amount of work that has to be done less or decrease the amount of effort that has to be applied. As a matter of fact, it's increased. But what happens? We can move this dumbbell over a very long distance. So this lever is actually designed for speed. But still, let's say, for example, that we take this bicep muscle and we move it out a little bit further to maybe, this would be kind of ridiculous, but let's just say we move it to 4. Now the mechanical advantage would be equal to 4 divided by 8, or that would be 1/2, and the mechanical advantage would be equal to 0.5. So if someone has just a slightly longer, from this we can see, point of insertion, what's going to happen? Well, in that case, now the mechanical advantage becomes 0.5. So the effort now is going to be equal to the resistance, 50 pounds, divided by 0.5. The effort's now going to be equal to 100 pounds. So if someone has just a slightly longer insertion point, it's going to make it easier to overcome this 50 pounds. We don't have to apply 200 pounds of effort. Now the individual has to only apply 100, the equivalent of effort equaling only about 100 pounds to overcome that resistance. So I hope that makes sense to everyone, and how insertion points and where the muscle attaches to the bone in the creation of the lever helps to create mechanical advantage. Okay, our third point that we said we were going to take a look at, our third principle, is the type of body movements that we have, or that we can see. All right, and when we talk about types of body movements, we're actually referring to a muscle's action. An action of a muscle is the type of body movement that's produced when the muscle undergoes contraction and pulls on the bones and causes body movement. Okay? Now, with that in mind, we basically have about 6 or so types of body movements. And let's go through each one of them. They usually work in pairs that we talk about them. The first 2 types of body movements we take a look at are flexion and extension. A flexion is defined as the reduction in the angle of a joint. An extension is defined as an increase in the angle of a joint. So anytime we're talking about a muscle action, we don't have to say that for this muscle or for that muscle, the action is to reduce the angle of a particular joint or increase the angle of a particular joint. We can say the muscle's action is flexion or extension. Okay, so when we talk about flexion, let's take the, if I can manipulate myself around here a little bit, let's take the elbow joint. And I can take the elbow joint, and now I can see the angle is about 180 degrees. But if I contract my bicep muscle, I can pull the angle of that joint to something less than 180 degrees, maybe 90 degrees. So I'm decreasing the angle of the joint. And when I decrease the angle of the joint, that's called flexion. On the other hand, if I contract the tricep muscle and I lower my arm back down, I can see that the angle of the joint has now increased to something near 180 degrees. So the angle of the joint has increased. When the angle of the joint increases, that's referred to as an extension. The next two terms we take a look at are elevation and depression. So elevation is defined as any upward movement in a single plane, and a depression, any downward movement in a single plane. So for example, I can take my shoulders and I can lift my shoulders up towards my ears. I'm lifting them up in a single plane. That's elevation, any upward movement. On the other hand, if I move my shoulders back down, depression. Elevation, depression. Got it? Okay. The next two movements we have are called abduction and adduction. And abduction is a movement away from the midline of the body or body part. Sometimes physical therapists and other clinicians refer to this as abduction to emphasize the ab part of abduction. Just to make it clear so there isn't any confusion, because when you say ab and adduction, if you say it quickly, people might be confused as to what you're saying. So oftentimes they'll say abduction. On the other hand, we have an adduction. An adduction is the movement toward the midline of any body part. So abduction and adduction. So for example, if I take my hand here with my fingers, I practice this all the time, I'm a big Star Trek fan. And so, when you think about Spock, live long and prosper. What did I just do with my fingers? I moved my fingers away from the midline of my hand. So that's an abduction, an abduction, a movement away from the midline. If I move my fingers back together again, I'm moving them toward the midline of my hand. That would be an adduction. So abduction, adduction, abduction, adduction. A good way to try to remember the difference between these two is that if I have my fingers spread this way and I move my fingers toward the midline, one set of fingers plus one set of fingers equals two sets of fingers. 1 plus 1 equals 2. I'm adding. That would be an adduction. Other examples of adduction would be if I take my hands and put them out straight, and if I move my hands down toward my side, I'm moving my hands toward the midline. That would be adduction. Okay, so I'm adducting the upper extremity. Or if I move my limbs away from the midline, that would be an abduction. And I can do the same thing with my lower extremities, or what we would commonly refer to as my legs. I can move them away from the midline, abduction. I can move them toward the midline, adduction. Next up, we have inversion and eversion. These two terms are reserved for talking about movement of the sole of the foot. So if we turn the sole of the foot inward, that's referred to as inversion. If we turn the sole of the foot outward, that's referred to as eversion. Now let's take my hand for example. Now this doesn't work with the hand, but let's pretend that my hand is my foot. Okay. Now if I move my hand in such a way that it points toward the outside, okay, pointing outward, then if that were my foot, we would say that I'm everting my foot. I'm turning the sole of my foot toward the outside. On the other hand, if I take my foot and move it in such a way that now the sole of my foot is pointing toward the midline or pointing inward, that's going to be an inversion. I'm inverting the sole of my foot. Remember again that those terms are used reserved for describing the movement of the sole of the foot. Okay, the next two terms we have are protraction and retraction. Protraction is any forward movement of a joint in a horizontal plane, while retraction is any backward movement of a joint in a horizontal plane. So I can take my shoulders again. Let's talk about those. And I can move my shoulders toward the front. I don't know how well you can see this in the camera, but if I move my shoulders toward the front in a horizontal plane, I'm protracting my shoulders. But if I pull my shoulders back, that's retraction, backward movement of the joint in a horizontal plane. Let me turn sideways and try to show this to you. So protraction of the shoulders, retraction of the shoulders. Protraction, retraction. Okay? Our next two body movements are pronation and supination. Pronation refers to the palms of the hand and turning the palms down or posteriorly if we're talking about the anatomic position. Supination, on the other hand, refers to turning the palms up or anteriorly. So let's say, for example, I take my hand, I have my hand here, and I take my hand and I turn it from this position over into this position. What have I done? I've conducted pronation. I'm turning the palms down or posteriorly toward the back. On the other hand, if I now turn my palm up so it faces up, I've conducted supination. So now my palm of my hand is supinated. And the opposite of that, pronated, supinated. A good way to remember that is if I can take my hand and drink soup out of my hand, it must be in a supinated position. If I can't drink soup out of it, then it's going to be in the pronated position. Okay? So I hope that helps. Our next two types of movement are dorsiflexion and plantar flexion. Dorsiflexion is the movement of the foot up or toward the shin. We're pulling the toes back, so to say. Toward the back means dorsal. Plantar flexion, on the other hand, is described as the movement of the foot in a downward position, somewhat akin to like stepping on a gas pedal whenever you're driving your car. Let's look at an animation of this. Hopefully this is going to work for us. Take a minute for it to come up. Okay, and we're going to take a look at the ankle joint and the movement of the foot. Ankle plantar flexion and dorsiflexion. So whenever we take a look at the ankle joint, here's the key we have to remember. That when we take a look at this joint, we have two sides. We got an anterior side to the joint, and we have a posterior side to the joint. Whenever we consider dorsiflexion and plantar flexion, we have to take a look at what's happening on one particular side or the other of this joint. So let's take a look at plantar flexion first. So we notice what's happening here in plantar flexion is that we're pushing on the gas pedal. Now, what we notice here is that, watch this as it continues along, this angle anteriorly is increasing, so that would be extension, but this angle posteriorly is decreasing, so that would be flexion. Well, that puts us into a quandary. Which side are we going to consider? Well, by convention, anatomists consider the back side of the joint when we're talking about plantar flexion. So let's carry this out a little bit further and see that as we continue plantar flexion, we can see that the back side of the ankle joint is flexing. The angle of the joint is getting smaller. And so that's what we refer to as this posterior side of the joint and how the angle is getting smaller. That's why it's referred to as plantar flexion, because you might be thinking, all right, I can understand the foot going down. Plantar is the underside, so we're going down toward the underside, but this angle is getting increased. Wouldn't that be extension? Remember, when we talk about plantar flexion, we're calling it flexion because this posterior angle of the ankle joint is getting smaller, and that would be flexion. On the other hand, if we take the joint then and look at dorsal flexion or dorsiflexion, notice that as the toes are being lifted back up toward the shin, the angle of the anterior side of the joint is getting narrower. When the angle of the joint is being reduced, that's referred to as flexion. We consider in dorsal flexion or dorsiflexion, we consider the anterior joint angle. Okay? So again, that angle's getting smaller. So I hope that helps you to understand the difference between the two. Okay, so let's pull that down and go back to our types of body movements. The next type of body movement that we have, these two don't necessarily work in conjunction with one another. They're singletons. The first one we have is what we call rotation. Rotation is the movement of a bone along its long axis or around its long axis. So the bone is kind of spinning along its length. Okay, so for example, I can rotate whenever I go from supinated to pronated. We can see that the radius and ulna are rotating along their long axis. Can you see that? Okay, so as I turn over, the radius and ulna are rotating. Okay, another way to look at this is we could take, let me try to reposition myself here. We can take the arm and put it into a flex position, and I can move my hand toward my chest. If I move my hand toward my chest, the way I do that is by turning the humerus on its long axis. I'm rotating the humerus to bring my hand in toward my body. Whenever I do that, that would be referred to as medial rotation of the humerus. Okay. On the other hand, if I turn the humerus in the opposite direction, such that my hand would move back away from my chest, that would be, once again, that's going to be rotation. That would be called lateral or sometimes external rotation. So external rotation here, internal rotation or medial rotation here. And then finally, we have circumduction. Circumduction is the movement in which the proximal end of a limb is stationary while the distal end moves in a circle. This creates kind of a cone-like movement. There are two joints in the body that are capable of circumduction via the contraction of various muscles. They are the ball and socket joints, the shoulder, and the hip. So for example, we kind of move away here. If I take my arm and stick it out to the side, I can draw a big circle at the tip of my hand, but at the end, at the root or origin, at the shoulder, notice there's not much movement. This creates a kind of a cone-like movement, and this would be circumduction. And I can do the same thing at the hip, circumduction. Okay? All right. And that takes us to our fourth principle that we want to talk about in this PowerPoint, and that is the principle of naming the skeletal muscles. To understand naming, we're going to look first of all at classification. So skeletal muscles produce movements, we know, by pulling on tendons, which in turn pull on the bones. So when we look at the muscles on the skeleton, they're arranged in such a way on a skeleton that whatever one muscle or group of muscles can do, another group can reverse. So whenever we talk about the type of movement that's produced, once again, we talk about the action of the muscle. Remember, the action of the muscle is the body movement that's produced when the muscle undergoes contraction. So we can classify muscles by their action. We can first of all classify muscles. We can refer to a class of muscles called the prime movers. This is also known as the agonist. The prime mover or the agonist is the muscle that's primarily responsible for the production of a particular body movement. Examples of prime movers might be the biceps brachii or the rectus femoris. So for example, if I want to flex my elbow, the biceps brachii is the primary muscle that's going to be responsible for me flexing my elbow for that body movement. So the biceps brachii is going to be the prime mover, the muscle that's primarily responsible for that movement, flexion of the elbow, or it's also referred to as the agonist. Okay, rectus femoris is a little bit harder for me to show, but if I want to flex my hip, or let's say better, extend my leg, the rectus femoris is going to be the primary muscle responsible for leg extension. And when we talk about leg extension, remember the leg is the part of the lower extremity below the knee joint to the ankle. So if I want to extend that part, you could try it for yourself. It's the rectus femoris muscle that's going to primarily be responsible for that. The rectus femoris then would be the prime mover or the agonist of leg extension. The opposite of the prime mover or agonist is called the antagonist. That's a muscle that opposes the action of the prime mover. Examples might be the triceps brachii, which is the agonist or the antagonist of the biceps brachii. So think about it. What does the biceps brachii do? Whenever it contracts, it's primarily responsible for flexing the elbow joint. Okay? On the other hand, once the elbow joint's flexed, how do we get the elbow joint to extend back out again? Well, either gravity or a muscle on the opposite side of the joint has to contract, in this case, the triceps brachii. So when the triceps brachii contracts, it's going to extend the elbow joint. It's going to oppose the action of the biceps brachii. Now you have to be careful about this. In elbow flexion, the prime mover is going to be the biceps brachii. In elbow flexion, the antagonist of elbow flexion is going to be the triceps brachii because it's going to extend the joint. However, if we're talking about extension, what's the prime mover of elbow extension, or what is the agonist? It's the triceps brachii. It has to contract. It's primarily responsible for extending the elbow joint. So now what becomes the antagonist to the triceps brachii? The antagonist is going to be the biceps brachii, because if the triceps brachii extends the joint, the biceps brachii is going to flex the joint. So you have to be careful about whether you're talking about flexion and what is the prime mover and the antagonist, or whether you're talking about extension and what is the prime mover or the antagonist. Okay. So we can further classify muscles by action by referring to synergists. So a synergist is a muscle or a group of muscles that help the prime mover by doing one of two things, either providing additional pulling force to overcome the resistance, or by stabilizing the joint, holding the joint steady, while the prime mover creates the action that we're looking for, the body movement that we're looking for. Some examples of synergists would include the vastus lateralis, the vastus medialis, and the vastus intermedius. I have a little bit of trouble showing this, but if you look at muscle plates and diagrams, you know that those muscles are three muscles that complete the quadricep group. Quadriceps include the rectus femoris, the vastus lateralis, the vastus medialis, and the vastus intermedius. So again, let's go back to I want to extend my leg. The muscle primarily responsible for leg extension is the rectus femoris. But I may have resistance associated with my leg at the ankle that's difficult to overcome. And so the prime mover, the rectus femoris, may need some help provided by additional pulling force. These muscles, the vastus lateralis on the outside, the vastus medialis on the inside, and the vastus intermedius underneath, will provide additional pulling force to help overcome the resistance, and as such, they are classified as synergists to the rectus femoris because they help the rectus femoris to overcome the resistance, to extend the leg. Now, the second class we have here are what we call fixators. Fixator is a muscle or group of muscles that aid the prime mover specifically by stabilizing the point of origin of the prime mover. Perfect example of this is the rotator cuff or the sits muscles. The rotator cuff or sits muscles are a group of muscles that lie in association with the shoulder underneath the trapezius and basically the trapezius muscle. There are 4 muscles involved in this. That's why they're called sits muscles. And these muscles are the subscapularis, underneath the scapula, the infraspinatus, the teres minor, and the supraspinatus. You'll be learning these muscles more in lab whenever we go over those muscles, or maybe you've identified some of them already. So what these muscles do is they extend from the torso onto the proximal part of the humerus. And whenever we want to, let's say, for example, carry out circumduction, these muscles kind of hold the joint tight so it doesn't wobble around while we're carrying out circumduction. And they hold it in place while other muscles like the deltoid muscle are the prime movers of circumduction. So fixators help to stabilize the joint while the prime mover moves the joint through its range of motion. It's important to note here then that whenever we take a look at the definition of a synergist, it's a muscle or group of muscles that help the prime mover by providing additional pulling force or stabilizing a joint. Okay, so with that in mind, we have to note here that all synergists are fixators. Okay, but whenever we take a look at it, okay, how do I want to say this? All fixators, an important way to remember this is all fixators are a type of synergist, but not all synergists are fixators, right? Because some synergists only provide additional pulling force, they would not be fixators. But those synergists that provide not only pulling force or they stabilize the joint would be referred to as fixators. Okay, and that takes us to our final principle and topic of discussion we want to take a look at, and that's the naming the skeletal muscles. So the question becomes, as you're looking at these muscles and you were naming them in lab the other day, you might look at them and say, how did they come up with these crazy names for the muscles? Can't there be simpler names for the muscles? Well, actually, those muscle names are the simplest names we can come up with, and not only are they simple, but they tell us a lot about those muscles. So we take a look at the skeletal muscles. Anatomists have named them on the basis of several criteria. Each of these criteria focus on a particular structural or functional characteristic of the skeletal muscles. So paying close attention to these cues, these criteria, can make it a lot easier to remember the names and the actions of the skeletal muscles. You might have to memorize less if you remember the criteria for which their names are based. So we're going to look at some of these criteria now. One criterion for naming skeletal muscles is the direction of the muscle fibers. Some muscles, as you can see here, are named in reference to some imaginary line, usually the midline of the body or the long axis of a limb or of a limb bone. When a muscle's name includes, for example, the term rectus, rectus means straight. Its fibers run parallel to that imaginary line. So, for example, when we think about the rectus femoris, rectus means it's going to be a muscle that has fibers that run parallel, or a strap-like muscle that's running parallel to the bone, the femur, down across the leg. Alternatively, the term oblique tells you a muscle's fibers run obliquely or slanted to the imaginary line. So we have the external and internal obliques, and you might recall from our lab that the muscle fibers ran in a slanted position. Okay, and so that's where one of them, the muscle fibers were slanted and they were located on the outside, external oblique. The other one, the muscle fibers, ran parallel to one another, but were slanted a different way, and they were underneath the internal obliques. Okay, our next criterion we have is the relative size of the muscle. So some muscles have in their names terms like maximus. So we have several muscles in a particular group or near one another, and they're over a particular body region or part, they may be divided based upon their relative size. For example, we have maximus, which means it's the largest muscle in that group, and minimus, which means it would be the smallest muscle in that group. So we can think of the muscles associated with the gluteal region. And we have a gluteus maximus, that's the largest one, and a gluteus minimus, which is the smallest one. And then we can also have terms like longus, which means long from Latin, obviously. And so if a muscle is a longer muscle in a group of muscles, it would be called the longus. Or if there was a muscle that was associated with it that was a little bit shorter, it might be called the brevis. Some examples of these are, as I said, gluteus maximus and adductor longus. In the adductor group, there are several muscles. One muscle is longer, and so it's referred to as the adductor longus. Another criterion for naming skeletal muscles is the location of the muscle itself. So some muscles are named for the bone over which they're located. Some examples of these would be the frontalis, which is the muscle that's located over the frontal bone of the skull, and the temporalis muscles, which is the temporalis is located over the temporal region or temporal bone of the skull. Next up, we have number of origins. So for example, we looked at that bicep muscle right at the beginning of this discussion, and we said the bicep muscle has two heads and therefore has two origins. One origin was on the superior rim of the glenoid fossa, and the other origin, or site of attachment, was on the coracoid process of the scapula. Two heads, two origins, bicept. Bi meaning two, sept meaning head. Triceps, on the other hand, three heads or three origins. The examples again are the biceps and tricep muscles of the arms. Each of these has either two bicep heads or three triceps heads. Another criterion for naming the skeletal muscles is the location of the muscle's origin and insertion. The location of the origin and insertion. And again, early on, we looked at a muscle called the sternocleidomastoid muscle. This seems like a long, ridiculous name to try to remember, but it's actually telling you a lot. It's telling you the actual origins and insertion of the muscle. So the sternocleidomastoid muscle, remember, has two sites, 2 points of attachment to more stationary bones, the sternum and the clavicle. So these would be the sites of origin. Sternum, clito, clavicle. And then it runs up along the neck and attaches to the mastoid process, the more movable bone. Sterno, clito, mastoid. The name tells you everything about the origin and insertion. So the next criterion for naming the skeletal muscles is the shape of the muscle. So for example, we have a deltoid muscle, the shoulder. Delt means triangular. So deltoid actually means triangle-like, or referring to a triangle. Next, the action of the muscle could be used in the name of the muscle. So terms such as flexor, extensor, adductor, these all may appear in the muscle's name. For example, you have a flexor carpi. Okay, flexor carpi. Flexes what? Carpi refers to the wrist. So a muscle that flexes the wrist would be flexor carpi. Extensor carpi is going to extend the wrist. And adductor longus is the muscle of the groin that when it contracts, it's going to adduct the leg or pull it toward the medial line. Okay, so that's our 4 principles that we wanted to go over in this PowerPoint. I hope you learned a lot from the PowerPoint, and we'll see you next time.